Hello, students, and welcome back to the Statistics and Mathematics Tutors course on Stochastic Processes 1. So, in today's video, we're going to look at some key distributions that are important in the study of Poisson processes. These distributions include the Poisson distribution, exponential, and the gamma distributions as they form the backbone of the homogeneous Poisson process. Let's dive into the video. So the first distribution is the Poisson random variable. So this in real world actually looks at the number of events in a fixed interval when occurs independently at a constant rate lambda. The PMF of this Poisson random variable is given by this expression, as you can see here, where k is the number of what records, or the number that we record in this fixed interval. Okay, this could be 0, it could be 1, 2, and so forth. Okay, let's look at some key distributions of this random variable. So the variance and then the mean of this Poisson distribution are all the same. And secondly, when you have two independent Poisson random variables, the sum of these Poissons will give us another Poisson with a rate lambda 1 plus lambda 2 respectively. That is, if we have the first Poisson process is with a rate lambda 1 and the second one the rate is lambda 2. Now, let's look at some key application questions and solutions. So the first one is that a call center receives on average 5 calls per hour. So what is the probability of receiving exactly 3 calls in the next hour? So over here we can clearly see that k is equal to 3 and our mean, which is lambda, is 5 per hour. So plugging it into the PMF, we simply get 0.14037 as our final answer. Also, a factory records 10 machine breakdowns per week on average. What is the variance of breakdown in a 3-week period? Remember, they told us that our machine breakdown, that is the lambda per week, is going to be 10. So that is very okay. Note that the variance is the same as the mean. So for a week, the variance is 10. 3 weeks will simply be 3 times 10, and that is 30. Okay. To our next question. In a bank, the probability of observing exactly 3 arrivals in 1 hour is twice the probability of observing 3 arrivals. Find the arrival rate, lambda. Over here, we need just two expressions. That's the probability of exactly 2 arrivals, that is k equals to 2, and that of k equals to 3. So that is what I've nicely computed over here. So now, the ultimate goal is to note that exactly 3 arrivals, the probability is twice 2, like 2 arrivals, the probability is twice that of 3 arrivals. Yes, so that's our equation of value. And when you realize by equating, the lambda here cancels with the e to the power negative lambda is common, so it cancels out. That's why you did not see it here. By simplifying this expression, we end up with what 1.5 per hour as our lambda. Next is the exponential random variable. So with this random variable, it looks at the waiting time between successive events in a Poisson process with rate lambda, which is positive. Now, one thing you should know about this Poisson, like the exponential and the link to the Poisson, is that with the Poisson, we are looking at the number of occurrences, like as in how many, okay, like as in 0 occurrences in a fixed interval, 1 occurrence in a fixed interval, and so forth. So now, the exponential distribution seeks to address the time, just the time it will take for this number to be recorded. That is what the exponential distribution does. Okay, so that the waiting time between successive events in a Poisson process is what the exponential distribution looks at. The CDF is given by this, and this PDF is given by lambda e to the power negative lambda x. Okay, and the solar function, which is actually the complement of the CDF. Okay, this is probability that x is greater than what small x, and this is the probability that x is less than or equal to a little x. Okay, so when you sum the two, you are supposed to get one. So one, they are complementary. Okay, thank you. So the moments are given below. That's the mean, and the variance is simply the square of the mean. As you can see over here, yes, the variance is the square of the mean. So now let's look at some the memoryless property of the exponential distribution. We're trying to say that given that x is above s, what is the probability that x is above s plus what t? The exponential distribution has a memoryless property, and this is how it goes. It does not recall its past events. Okay, as in it does not recall the given that a conditional event means that something has already happened. So that x greater than s has happened. So it does not recall it. Whatever it can recall is only the t, the extra t is added to the s. Okay, yeah. So this is the same as what probability that x is greater than t. So it does not recall this s, the conditional event. Okay, thank you. So let's try to see and verify this memoryless property. Okay, so now you realize that okay that the conditional event of the memoryless property can be seen as the intersection of these two intervals divided by what probability that x is greater than s. But now let's see which one is the ideal intersection. Probability that x, so from this diagram timeline, you realize that x greater than x greater than s actually starts from this point to infinity, and then x greater than s plus t actually should move from this side, that is to infinity. Looking at it, you realize that x greater than s plus t can be found inside x greater than s, and hence the intersection becomes x greater than s plus t. That is how we have it over here. And as you can see, these are all survival probabilities. So we substitute this into the survival function, and we end up getting these two expressions divided. And from your indices class, you realize that this one can be separated as e to the power negative lambda s times e to the power negative lambda t. So the down, that's the negative lambda s will cancel with the top, leaving us with e to the power negative lambda t. And this is simply what? The survival function at t. So that's the verification of the memoryless property. So let's look at some conditional moments of the exponential random variable. So I'm saying that if x, given that x is above some point, that is a real number, a, okay, the moment or the expected value of x is simply the expected value of the normal exponential random variable, that's the expected value of x plus that real number. It's simple as that. But if we subtract the real number from x and we find the conditional expectation, we simply get the same random variable as x, and as much the mean will be the same. For variance, it is not affected by linear transformation, as you can see in this two. So whether it's this or that, the variance is going to give us the same thing as the square of the mean. These are very powerful tools for analyzing lifetime and reliability. Let's look at some questions under this domain. So a critical server experiences repair times that are well modeled by an exponential distribution. Historical data shows the mean repair time is 2 hours. So now we know the mean is equal to 1 over lambda. So meaning by substitution we realize lambda should be equal to 1 over 2. That's the inverse of the mean. Now we have the PDF, the survival function, all are given to us, and as we know, the mean is 2. So the variance will simply be the square of that. So they are just giving us some properties of the distribution so that we can answer this follow-up question. So given that the server has already been under our repair for 1 hour, that is like given that x is greater than 1. So what is the probability it will be repaired within the next 30 minutes? So remember, we have already spent 1 hour. That's like probability that x is greater than 1.5, given that x is greater than 1. Okay, and as we all know, that one will just give us the probability that okay, sure. I think because they said within is like less than or equal to, so we are going to have the CDS instead. So given that x is less than or equal to 1.5, yes, giving this survivorship at 1. So we know that the CDF and the survival function are complement. So this is the same as what? So turning this into what? A survival function, that's x greater than what? 1.5, and we have to take the complement of that. So that will simply give us what? This side will give us probability that x is greater than 0.5. So that will give us this, and that's the answer. So as we plug the lambda, which is 0.5, as we saw from the above, that is 1 over 2, we're going to get 0.2212 as our final answer. Let's look at the next one. So given that it has already been under repair for 1 hour, what is the expected additional repair time in the variance of that additional time? So we all know this is given that x is greater than 1, the expected value of what? X, given that x is greater than 1. Okay, this is the same as what? 1 plus the mean of the normal exponential rounded error, which is 3. Let's confirm that from the solution. So as you can see, this is x, expected value of x, given that x is greater than 1, and that would simply be what? 1, which is the real number, plus the mean of the x, and that is what? 3 hours. The variance, simply, variance is not affected by those linear transformations, so it's going to be the same thing. The conditional variance will be the square of the mean, that is 4. All right. Let's look at the last one. So what is the probability that the repair completes within what? 3 hours from start? That is probability that x is less than or equal to what? 3. That is within 3 hours. So probability that x is less than or equal to what? 3. So let's look at that. So with that, we just plug 3 inside the CDF function, and we're good to go. We get 0.7769 as our final answer. Alright, so let's look at the gamma distribution. So actually, with a gamma, it looks at a combination of what? Independent exponential random variable, as in if you sum 2 or more independent exponential random variables, you simply get the gamma distribution. So that is why we say that it looks at the waiting time of a Poisson process. Okay, where k is the shape parameter for the gamma distribution. Okay, yes, so the PDF is given by this expression. Okay, yes, and the expected value of the gamma, because it's independent exponential, so the mean of this k independent exponential distribution will be summed up k times to get us the mean of the gamma. So that will just simply be what? 1 over lambda plus 1 over lambda plus 1 over lambda k times, and that will just be k over lambda. And this one we're going to have 1 over lambda squared plus 1 over lambda squared, summing it k times will give us what? K over lambda squared. Okay, so for special cases, if k is equal to 1, we have the exponential distribution, as I've already said. If k takes integer values, then it becomes the Elan distribution. That means that the gamma, if this k becomes strictly integer values, as in 0, 1, 2, 3, and so forth, not taking real numbers, as in 0 point something, those kind of real numbers, then it becomes the Elan distribution. Also, note that gamma of the integer values is the same as what? Is the same as, that's k minus 1 factorial. That's what you need to know. Yes, yes, you need to know this. So if gamma of k should be equal to what? K minus 1 factorial, if k is an integer value. Yes, simple as that. Okay, let's proceed. So let's look at some questions. It said that the time until the first bus arrival follows gamma with what? K being 1 and lambda being lambda. So show that this is just an exponential distribution. So all we do is to plug 1 at k, and you can see that what lambda to the power 1 is lambda, as you can see here. X to the power 0 will give us what? 1. Okay. Then e to the power negative lambda s is there. You can see it's already the exponential PDF. But let's see the gamma 1. Gamma 1 will be, once 1 is an integer, this will be equal to what? 1 minus 1 factorial. So 1 minus 1, which is equal to what? 0. So that will be 0. Sorry. So that will be 0. And we know 0 factorial, right? 0 factorial is 1. So that is why the division, the denominator is also 1 as well. So it doesn't affect anything. Thank you. Let's proceed to the next question. So suppose buses arrive at a station with rate 2 per hour. What is the what? The expected waiting time until the third bus arrives. So me, the arrival rate is 2, that is lambda, and then our k is going to be 3. So what is the expected waiting time? So we know that expected waiting time will be what? K over what? Lambda. So that's 3 over 2, 1.5 hours. If you want to find the variance, that will simply be 3 over what? 2 squared. That will give us 0.75. So yeah, but they did not ask for that, so it's fine. Okay, sure. So now let's look at some linkage. When it comes to the gamma distribution, usually um, finding probability values or probability computations become very difficult because of its nature. So it has a relationship with the Poisson CDF. Okay, so if you want to find a probability that x is less than or equal to little x, that is capital F of x, is the same as what 1 minus a Poisson random variable with a mean. So the mean of this Poisson is going to be lambda times that x. The rate for the lambda is just going to be lambda times that x. Okay, everything will be the same as we sum j round from 0 to k minus 1. This k is actually the k over here. That is the, in our previous example we had 3. So in this case it could have been what? 3 minus 1, which is 2. So we are going to sum a Poisson random variable where j round from 0 to 2 in that case, right? Good. So this is very important. This shortcut is very, very important when you have to compute the probability values of what the gamma distribution. Okay. So note the the survival function will simply be what? The complement of this, and that will be um everything here with the exception of the 1 minus. So everything, this one will go away. It will just be summation as j round from 0 to k minus 1 of this the was the PMF of the Poisson. Alright. So this expresses the gamma CDF in terms of what Poisson tail probabilities, as I've said, right? Good, 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 good. So we can see that at different times that we want for the exponential random variables, we have the independent, these are interarrival times, okay? So the interarrival times follow what? Exponential. So x1 is exponentially distributed, x2 and x3 as in that order. Okay, so when you sum these three up, you're going to get a gamma distribution because these are more than what, like 1 exponential. So that T3 becomes a gamma distribution with k equal to 3. All right, thank you. So now let's do a wrap up of this video. Okay, so we've seen that the Poisson counts the number of events in a fixed interval, then the time until the next event, the time, underline this, the time, yes, follows the exponential, and the time until the case event, that means independent exponential becomes a gamma. So together they form the backbone of the homogeneous Poisson process. So we've come to the end of this video. Thank you so much for your patience and understanding. In our next video, we're going to look at just questions on the Poisson process. Okay, yes, this is a review, and there's a video on the Poisson process on this one. Okay, sure. So we look at the Poisson process and we solve questions in that order. Thank you so much. Have a lovely day. Bye.